Hi everybody! In this video, we are going to talk about a few more things about equilibrium constants. So first, let's talk about how we can convert between Kp and Kc. So here's a very straightforward equation. Kp is equal to Kc times parentheses RT parentheses to the delta N for gases. So the delta N for gases is the change in the moles of gas. So to get this, you simply do moles of gas in the product side minus the moles of gas in the reactant side, and that will yield the change in the moles of gas. So, if you remember, Kp involves an equilibrium expression where everything is in pressure, while Kc is an equilibrium constant that involves everything in molarity. So now I will prove this equation. So to first prove this, we need to use the ideal gas law, PV equals nRT. So we can move things around and we divide both sides by V to get P is equal to N over V times RT. Now we know that moles over volume is equal to molarity, so substitute N over V to get M, and we get that pressure is equal to molarity times R times T. And remember that R will be 0.0821, and our T will be in Kelvin. Now, let's write a generic reaction to demonstrate what Kp stands for. Kp is equal to all this, as you might know, and you could substitute P for mRT. So here, for Pc, for example, the partial pressure of C, you could substitute it for the concentration of C times RT, and that's what I did here. The concentration of C times RT is equal to the partial pressure of C. Now, of course, we're still raising it to the C power because that's the coefficient, and you do that for all the partial pressures. Now, let's simplify this even further by taking it apart, by distributing the C to here and to the RT. And if we distribute the C to the concentration of C, we get this. And if we distribute the C to the RT, we get this. Now, you do that for all four of them, so let me do it again. D distributed to the concentration of D, right there, and D distributed to RT, over here. And you do that two more times to get this entire expression. And notice how this right here, the thing I'm boxing, is actually Kc, because Kc is everything in terms of concentration, which is what we have here. So Kp is equal to Kc times RT. So over here, on the right side, I'm going to start combining exponents since they all have a common number inside the parentheses. So you know that if they're multiplying, you're going to add them, and if you're on the bottom or on the denominator, that means you're going to subtract them. These are just simple exponent rules. So RT to the C times RT to the D is going to be RT to the C plus D, and then divided by RT to the A times RT to the B. You have to subtract A and B. And we can simplify this by factoring out a negative to get C plus D minus A plus B and keep everything else the same. And we know that C plus D is the moles of gaseous product because C and D are our products in this reaction. And A plus B are the moles of reactants. So moles of gaseous product minus moles of gaseous reactant will equal the moles that changed, or the change in moles final minus initial. So Kp is equal to Kc times parenthesis RT, all to the delta Ng. Now let's do a practice problem with that equation that we just learned. So here is the equilibrium reaction between dinitrogen tetroxide and some nitrogen dioxide. So you have to balance it, of course, and we did that for you. So a nice little reminder I want to give you is to always balance your reactions before you begin. Now, the Kp of this reaction is 11, and that's at 25 degrees Celsius. Now, we have to use this equation somehow, and it seems like we have all the information we need. we have Kp is equal to Kc, the thing we're trying to solve, times R, which is 0.0821, times T, which is in Kelvin, and 25 degrees Celsius is 298 Kelvin, and the change in the moles of gas is the moles of product gas minus the moles of reactant gas. So, we have 2 moles of gaseous products, and we have 1 mole of gaseous reactants. 2 minus 1 is equal to 1. So, that's why we have 2 minus 1 here, and you simplify it, and you get that 11 is equal to Kc times 24.5 to the first power. Now, we can rewrite this, and we can conclude that Kc is equal to 0.45. So that's pretty cool, and you use that maybe if you're given concentrations of these substances instead of their partial pressures. So it is very helpful to know this equation, and now let's move on. So we have this really cool equation called the Van Hoff equation. This is a cool equation, as I just said, and it's related to the Clausius-Clapeyron equation and the Arrhenius equation. So this will be familiar if you learned about those things, and if you haven't, well, welcome aboard, I guess. So this equation tells us that the natural log of the equilibrium constant, doesn't matter what type, it's just any equilibrium constant, is equal to the negative of the delta H of the reaction, either in joules or kilojoules per mole, and you divide that by R times T, and if you chose joules here, then you will use 8.31 joules per mole times K for R, and if you chose kilojoules per mole, you will use 8.31 times 10 to the negative 3 kilojoules per mole times K. And note that these two are exactly the same thing, except this is in joules and this is in kilojoules, and that's maybe the reason why we have a 10 to the negative 3. So we do negative delta H over RT plus something called delta S over R. Now, we will learn about delta S, or the change in entropy, in Unit 11. So ignore this if you don't know it, and if you do, that's great. Now, keep a note that delta H and delta S are mostly constant at any temperature, and this is just an assumption because yes, they do change, but for our purposes, we are going to assume that they will not change, and that will be further discussed in Unit 11. And therefore, the only changing things in this equation will be our T and our K. So, if you notice, this equation is graphable. You can make a line. So, if we graph L and K, which could be our y-axis, and 1 over T, or over here, as our x-axis, then the slope will be this part, or negative delta H over R, and our y-intercept will be delta S over R. So if you ever have a graph that is graphing the natural log of equilibrium versus 1 over T, you know exactly what to do to find the delta H and the delta S. And we will talk about this more in a future video, as I just said. So, we need to use this equation mainly because we might want to calculate K at 2 different temperatures. So how do we do that? Well, we can have 2 points, so T1, K1, and another point such as T2, K2, and we can actually write the equation for K2 and K1. So for K2, of course, you just chug it into that equation, and you will have T2 to correspond with K2. Now we can do the same for K1 with a corresponding T1, and of course everything else is constant. And notice how we can create a system of equations, and you might have seen me done this before, so if you have, great job. So we actually subtract these 2 equations, so we get the natural log of K2 minus the natural log of K1 is equal to the delta H of the reaction over R times 1 over T2 minus negative delta H over R times 1 over T1. And doing some simplification and some log rules, we can say that the natural log of K2 over K1 is equal to negative delta H over R times, parentheses, 1 over T2 minus 1 over T1, and parentheses. So notice how this equation looks very similar to some other equations we derived in the past. And that's because they're all related in some way, and that's pretty cool. So this equation lets you have an initial T and an initial K, and if you ever change the temperature to a new temperature T2, you will be able to calculate the K2 corresponding to that. So it's pretty cool, and let's actually not use the equation to do a problem, but we are going to explain one of Le Chatelier's principles, which says that increasing T increases the K of an endothermic reaction. And in addition, increasing T will move an endothermic reaction to the right at equilibrium. So before we do math, let me show you why that happens exactly. So let's just say we have a reaction going from A to B, and the delta H is going to be positive because it is endothermic. So that means heat is going to be on the left side. So we learned that in Le Chatelier's principle that if we increase the temperature, we are shifting a system at equilibrium to the right. So a system at equilibrium will start moving to the right once you increase the temperature of that endothermic reaction. Now, why does this happen? Well, let's think about this for a second. So let's just say that this reaction has a K of maybe 1, all right? And let's just say that the system is at equilibrium. If the system is at equilibrium, that means that the ratio between the products and reactants will be equal to K. So Q is equal to K, because remember, Q is a reaction quotient. It's telling you the ratio between products and reactants. And if the ratio between the products and reactants are at equilibrium, that means that Q must equal to K. So now that we know that, what happens if we start increasing the heat? So if we increase the heat, we know that our equilibrium constant will increase according to the thing we just said over here, that increasing T increases the K. So we know that, and we know that our K, or our K prime, which I will label with a prime symbol, will be bigger. So it might be 3, for example, because increasing T for an endothermic reaction increases K. But think about this. Our products to reactants ratio, immediately when you increase the temperature, is still going to be the same. So our Q is still equal to K before, which was equal to 1. But if you increase the temperature, the K is a lot bigger, and now your Q is less than K. What happens when Q is less than K? Well, we know that the reaction will go forwards. So let me actually relabel this. So let me put double arrows here, and let's put a single arrow there to indicate that the reaction goes forward. So before, we were happy and at equilibrium. But once you increase the temperature, the K increases, and now your Q is less than K. And because your Q is less than K, then the reaction will move forwards to restore equilibrium. And that's why increasing the temperature of an endothermic reaction at equilibrium shifts the reaction right. Now you could apply this logic for exothermic reactions because it does the exact opposite. So now that we've proved that increasing the temperature of a system at equilibrium that is endothermic will shift the reaction forwards, let's prove why increasing temperature actually increases the K of the reaction that is endothermic. Now, sorry for this weird line down here, but I don't know, it's just glitching, and that's fine. So, let's just assume that the delta H of this endothermic reaction is positive, and that's what it means to be endothermic, by the way. And we will assume that delta H is positive 100 kilojoules per mole. Now, we can have the information that we are going from a lower temperature to a higher temperature, so we are increasing the temperature, and this is just an example to prove something. So, the natural log of K2 over K1 is equal to the negative of the delta H over R times 1 over T2, which is this, minus 1 over T1, which is this. And doing some nice and fancy math and keeping track of sig figs, and we kept track of sig figs until we got here, because we needed to solve e to the 60 point. And this is the inverse natural log. And for inverse logs, we have to take the number of decimal places and make that the number of sig figs. There are no decimal places, so there will be no sig figs. And that's not what we want here. We want to have an actual number. So because of this, I'm going to ignore sig figs here, because my answer will have 0 sig figs if I simplify this anti-log. So let's ignore sig figs, and we get that K2 over K1 is equal to 1.1 times 10 to the 26 for this reaction. So by going from 100K to 200 Kelvin, the equilibrium constant was multiplied by this gigantic number. Wow, right? So in general, we proved that increasing temperature increases the K for endothermic reactions. Now what about an exothermic reaction going from 100K to 200K? So we're increasing the temperature for an exothermic reaction. What will happen to our K? So we assume that delta H is negative 100 kilojoules per mole, and we do the same exact thing we did up there, but we use negative 100 instead of positive 100. And I got that K2 over K1 is equal to this extremely small number. So by going from 100 Kelvin to 200 Kelvin, my equilibrium constant diminished by a lot. So, as you can see, K2 over K1, or the ratio between the equilibrium constant after over the one before, is this super small number, and this tells us that K2 is pretty small compared to K1, which means that increasing the temperature decreases the equilibrium constant of exothermic reactions. So I hope you learned a lot in this video. I hoped you gained a lot of insight into the concepts of equilibrium. And that's all for this video. I hope you have a nice day, and adios.